removed. 13th question. Okay. You see, can everybody see the 13th question that is in the WhatsApp, or if somebody is unable, I have to open the WhatsApp.
Yes, sir.
Better will be need to ask whether or not anyone cannot see. Is anyone facing a problem to access the WhatsApp? In that case, I can share, or just a small question, I can read it out. Okay, let's see the question itself.
Sir, please.
Repeat.
Sir, if you please read it out. Actually, I don't have.
Okay, fine, no problem. The question is saying.
Yes.
Oh, Rishabh. ठीक है. Tonight you'll get it, Rishabh. Fine. I'm actually going to that time, but some other problem came up over there. Get it tonight, okay? Or maybe if it is not done by tonight, I'll just post in the group, and some people, maybe Nilavata can do that, or Ankit, or anyone can do it, okay? But only after I am unable to give time to it, okay? If I'm able to give a time, I'll just do that. Okay, the question in this case says, there's a raindrop. Raindrop falls from great height actually. So what happens is, as they fall, usually when raindrops are falling, what happens is they experience, apart from the gravitational pull of the earth, the constant gravity, apart from there, they also experience two other forces. One is the buoyant force and the other one is the viscous drag actually. Fine. Usually in this case, we can for the moment neglect the buoyant force over there. So we can consider only two forces which act on. Yes, Shekhar, good evening. Actually, when I started recording, it showed me that you'll be logged out, so that's why I told you. Okay, it happens when there's some network issues actually. Okay. If you just consider a raindrop which is falling, let's say for the moment we neglect. Sahad is presenting. Okay, go ahead, do that. But I think I'll just read it out. Doesn't matter, Sahad. Ryan, good evening. Okay, let it be on the screen. You have removed it. Okay, that's fine, no problem. It's okay. There's no issue. I will just read the question. Okay. Just first the question itself. Now the question is saying, it is from NCERT, I believe, 6.13 in fact, chapter 6, question number 13. The question says that a raindrop of radius 2 millimeter falls from a height of 500 meter above the ground. So this radius is 2 millimeter. So diameter becomes 4 millimeter for this raindrop. That's 4 millimeter. It just falls from a height of 500 meter actually. So Abhirup, good evening. Yeah, 500 meter is obviously very large compared to the size of this raindrop. So we could just forget about the radius when we consider the motion of the raindrop itself. It behaves like a point mass actually. So what's happening is this raindrop is falling from 500 meter off the ground. It falls with a decreasing acceleration due to viscous resistance of the air. The air exerts a viscous drag, a viscous force, which is proportional to the velocity actually. And because of that, the speed, the acceleration rather, decreases. Initially, the acceleration is going to be just g. If I neglect the buoyant force actually. Initially, the acceleration is simply g, but as it speeds up, there's a velocity coming up, and then there will be also resistance coming from the air, which is actually proportional to the velocity itself in the opposite direction. So that resistance, in fact, will increase gradually. If you look at the beginning, there will be only one force, which is nothing but gravity. That's the only force which acts, which is a constant over there. The other force which comes up over here is a force proportional to the velocity. K into V is what I have written down. This force is proportional to velocity. It will be initially small because initially the velocity is small actually. So it is initially going to be very small. which implies that mg is still more. Mg is still larger compared to that force, and therefore the acceleration is still down. But because the acceleration is down, the speed will increase. But as the speed increases, in that case, kV increases as well, so that the net acceleration decreases actually. But as long as the acceleration remains positive, decreasing or non decreasing doesn't matter. But as long as the acceleration is downward, the speed will increase. So the speed continuously increases, so this vector grows continuously. The backward force is increasing, and at least after a while, what will happen is this kV will become large enough so that this mg is going to be exactly neutralized by that kV, the resistance over there. Once that happens, net force turns out to be zero. Because net force is zero, the acceleration becomes zero as well. Because the acceleration is zero, the speed no longer increases. So that after that, therefore, it will just move with a particular fixed velocity, a constant speed subsequently, which we call as a terminal velocity actually. Okay, that's known as a terminal speed or terminal velocity, with which the raindrop will fall after a while, in fact. So the question in this case says that it attains its maximum speed and moves uniform speed. Okay, half its original. By the time it has gone down half its height, which implies 250 meter, at that point of time it acquires the terminal velocity, and then it moves uniform speed. The question is asking what is the work done by the gravitational force on the drop in the first and the second half of its journey. What do you think about that? We are being asked the work done by the force of gravity on the drop for the first half of the motion, which implies till it was this accelerating downwards, and for the second half of the motion, where it is moving at uniform speed. Okay, so what will in this case be the work done by gravity in the two cases?
So it will be mg.
It will be same as the mg into the height 250 meter in both cases, by the way.
The first,
Again, repeat. I could not get you.
so in the first part I didn't have any problem. In the second part I had some problems.
What problem? You see, be very clear about the definition. The work done by any force is by definition force into displacement in the direction of the force. So you have to find the work done by the force of gravity. So it is simply gravity mg multiplied by distance, as simple as that.
No, sir. I was talking about the second question, not the first question.
Oh, sorry. What is the work done by the resistive force in the entire journey? So what do you think? What is the work done by the resistive force in the entire journey if its speed on reaching the ground is 10 meters per second? What do you think about that? Apply the work energy principle. There are only two forces which are acting on a drop. One is the force of gravity, the other is resistive force. So we can say work done by gravity plus work done by the resistive force should be equal to the increment in the kinetic energy only. Because in this case, I'm not taking the gravitation potential energy.
Sir, will it be plus or minus?
What?
Sir, it should be minus, means work done by gravity minus.
No, that's not correct. The work energy principle is very simple. The total work done by all external forces.
When we will be writing the direction, then means we have to give the negative sign.
No,
Right,
I mean, see, it will automatically come out to be negative if it is negative, okay? The idea is pretty simple. Work done by all the forces. Now, work we have to calculate by the gravitational work, I know. It will be nothing but mg into total height is positive. Work done by entire forces, this would be equal to delta k, as simple as that. That will consist of work done by the gravity, which is mg into the total height, 500 meters, plus work by the resistance force. The resistance force I do not know yet, but I just do not require it either. It will, strictly speaking, a force which will vary with velocity actually. It doesn't matter. It will work by the air drag, air resistance. That should be equal to delta k. That is what we have. So that will give us directly the work done by the air equal to air resistance rather is delta k minus mgh. It will automatically give you the required result. No need to just take extra the sign of this entire thing. Okay. If you write down explicitly the work done by the air resistance, then you have to just take the minus sign. But in this case, not. And it is not going to be good. Okay, on it if you just so put a minus sign over here. Just have some patience on the laws, on the equations over there. It will give the required result as long as you do it correctly. Okay. In this case, for example, I have this particular equation from the work energy principle. And we can see over here that it will actually come out to be negative on its own, because delta K is final minus initial. Initial kinetic energy is 0. I'm considering the entire journey actually from the top to the bottom over there. So in this case, delta K is going to be simply the final kinetic energy, because the initial is simply 0. I get therefore half into m into v final, which I know, minus mgh is what I have. Is the mass given in this case? The radius is known. Okay, we can obtain in this case, no, the mass is not given. We might have to use the density of.
So
what the point
mass
is.
we can
have to
find
do
it
that.
using the
It's water
density and the
activity, so we
volume.
know the density.
So I had done that.
So and we know we have been given the radius. We can find the mass. A bit of calculation involved. How much is the mass, by the way? Let's see. It is the radius is 2 millimeters, isn't it? We get 4 by 3.
So it's coming 3 point something into 10 to the power 3.
What? It's a 2 millimeter drop.
3 point something into 10 to the power minus 5.
Kg.
It was coming. Yes, sir. Kg, in kg.
Still, I have got a calculator, so let's verify. 4 into pi divided by 3 into radius cube. 2 millimeter is what you have. So we get 2 10 power minus 3 whole cube, in fact. 2 3 whole cube. Okay, that's pretty bad. Into density is 1000 kg per meter cube. Yeah, that's fine. It's approximately 3.4 10 per minus 5 kg, isn't it? The mass is 3.4 10 per minus 5 kg roughly. V is 10 given, so 100 by 2 minus G is 10, or are you supposed to take 10 or 9.8? Less than 9.8 is what I take up. In any case, I'm using calculator, so it doesn't matter much. That makes it 50 minus the entire thing, and the mass is 3.35 3.35 or 3.4 is better to take it up. 10 power minus 5 kg, and 50 minus roughly 5,000 what we have. So that will give us in this case a negative minus 4850 what we have actually, multiplied with 3.4 in power minus 5. That gives us negative minus 0.165 joule approximately. The work done turns out to be finally around minus 0.165, or you can say 0.17 if you wanted. Well, 1.16. 165. That's what I'm getting, in fact. Okay. Can you check the answer what is given? It doesn't matter. There's the idea, at least you can just look at the calculation part over there. Okay. Is it fine or not fine?
So, sir,
No.
can you please explain this one once more? I just joined due to this net problem.
Can you see the question?
Yes, sir.
So the second part of the question is what we have. The question was asking to find out the work done by the air resistance force if the raindrop strikes the ground with a speed of 10 meters per second. Fine. So I utilize the work energy principle for the drop only. I consider drop as my system, so that there is only the kinetic energy involved. Everything else is external force. Like in this case, we have the viscous force as well as the gravitational force, mg. So I utilize the work energy principle, write down the work done by the external forces, which involves that of gravity, mgh, and that of the air resistance. These two together, this should give us the increment in the kinetic energy that we can calculate, because we have the initial kinetic energy 0. The final is nothing but half mv into, v is 10 meter per second square, so we get half into m into 100 in SI unit, where m has to be calculated because the size is given, so you can calculate the mass of the raindrop.
Okay, sir.
These are the
Understood.
equation that we have. Okay.
Sir, understood.
Okay, fine. Only you can finish it now.
So if we do this using the means change in mechanical energy equals to force external, then can we show
That
that
would also
it
do.
by that?
That would also do. In that case, the external work will be just that of the air actually. Anna. So we can write down the work done by the air resistance. That should be equal to delta E, the mechanical energy this time. Delta E implies the final mechanical energy and the initial. So the final mechanical energy consists of the final kinetic energy, while the gravitation potential finally becomes zero. U final I could write down. Then minus initial one is just zero and initial energy. So because the final is known half mv final square, this part is zero minus half mv initial square is zero, and this one is going to be mgh. We end up getting the same equation back. I have half mv final
Okay,
square
sir.
mgh. Yeah. Enough. As long as you apply the same equations correctly, you will get the same result. The same thing I've got over there. It's fine.
Yes, sir.
Okay. Anik, I said you could stop the presentation now. Okay. Anyone? Anything else? Rahul, you have sent a question yesterday. Acha, you sent it. Okay, I was thinking who has sent because the number is not saved in this particular mobile actually. It was here, I believe. Well, can you forward in the group, Rahul? Now, just forward the question in the group. Okay. Not yet come. It has not yet reached me. Now it has gone. Yeah. Now it has come. Let us see. The question number 55 is what you want? Okay, Rishabh, Newton's laws of motion you can just send as well. Yeah, 55. Acha, fine. No problem. Have you people done the questions from this Dr. A.C. Verma book, Concepts of Physics? You should do that. NCRT first, and once you finish the NCRT part, then you just go to that book by, Dr. A.C. Verma, which is, I think you should have it, Concepts of Physics, isn't it? Especially do those beginning objective questions, okay? I know Rishabh, and I also know that this Rahul question is also in HC Verma over there. But anyway, the point is that at least do those MCQs which are given in the beginning, okay? No, it is there actually, Rahul, though it is not from this book, but it's also there actually. I mean, you can't now point out the source anywhere, by the way, because they are all coming from different, say somewhere over there. Anyway, I was just saying that after every chapter, just try to do the MCQs which are given at the end. They are especially good conceptually, actually. If you are able to do them comfortably, it implies that you have understood the concepts. Otherwise, there is a big problem, actually. Okay, then you might not do all the questions of the numerical part, but at least you might say that, okay, let's say do the odd number questions or even number question you can attempt later on. That way you have to manage, but at least you should do most of the questions from that book actually. They're useful in forming the concepts over there. I personally, I have not done it, but I know many people have asked me the questions, so I can. Okay, Rishabh, you can send me. You send me, I will check it out. I'll first take Rahul's question and then you one, okay? This is Ryan, I believe. This is a question which is
Yes, sir.
I've done many times over there. Anyway, no problem. I can just do it. It was in my mind, and I think I answered this question for somebody earlier. No problem, Shakul. First of all, Rahul's question. So the question says that a body is suspended on a spring balance in a ship. There's a ship, and in the ship there's a body which is suspended from a spring balance, which is in effect a spring. So I'm just drawing a spring over there, and it weighs W. So when the ship is at rest, it is showing at rest with respect to what? With respect to the water, actually, which implies with respect to the earth, the ship is stationary. It is showing the weight of W when the ship is stationary. Stationary is implicitly implying that it is stationary with respect to the earth, okay? Or to be more proper, with respect to ocean, but we can assume in this case. Ayush, yes, if you are solving I Rhodope, it is more than enough, by the way. Only thing is that, I mean, say, as far as I'm concerned, is more than enough, definitely. But you must do every question carefully, okay? Just not try to bring the answer only. That is not how questions should be done. But at least you can start. You will find going to be Nilabrata. First, let us see how long it takes. I will solve everyone's doubt. Just don't worry. When stationary, the weight is W. Now the question says when the ship begins to move along the equator from west to east, the ship is moving along the equator. No, Shubham, it is a very common question which you can find in most of the books, actually. Just wait, by the way. Okay. So the question says when the ship begins to move along the equator from west to east direction, you will see that the Earth also rotates from west to east direction, actually, isn't it? The Earth is rotating from west to east, so the sun seems to rise along the east and sets in the west. With a velocity v, this is again with respect to the Earth, right? The scale reading is approximately equal to how much? The angular velocity of the Earth is given to be omega, right? The question is this: you have over here a ship which is stationary, and inside the ship there's a spring balance, which is from where we have suspended a block whose weight, when the ship is stationary, is shown as W. Notice in this case that though the ship is stationary with respect to the Earth is still rotating, actually. So strictly speaking, the spring will be elongated a bit. In fact, it will have to be elongated in any case, by the way, because it's going to support what? From an inertial perspective, if you consider what will happen, I mean, we can just write on W equal to nothing but mg to begin with. If I just neglect the Earth's rotation then. But with respect to the Earth, if I consider, I mean, if we just we look at the situation from an external reference frame where the Earth is seen to be rotating, then there will be a slight different reading over there. Or the question, Tyasa, or the what I was saying. What I was saying is we should better look at the entire thing from the perspective of an observer, who is looking at this system from beyond the Earth, actually. Okay, let's take up an inertial reference frame. I just take up the part which is I just take up with respect to an observer who is outside the Earth. So the Earth is rotating, in fact. So when the ship is stationary with respect to the Earth, with respect to that observer, it is not going to be stationary. It will be moving, in fact, isn't it? Because the Earth is rotating. Look at, say, for example, the top view. I'm looking from above the North Pole. That is, we are looking from above the North Pole. So North Pole is coming towards us, actually. North Pole comes towards us, and the South Pole goes beyond us over there. And maybe, let's say that this is rotation sense of the Earth, which I'm arbitrarily taking as west to east. Fine. So if I just look at the ship, for example, over here, there's a ship, a small vessel that we have. Say, for example, this is a ship actually. This ship will actually seem to move with respect to this observer, isn't it? If I consider the reference frame, which is the Earth itself, then obviously in that reference frame, the ship is going to be stationary. However, if I consider it from the observer who is looking at this from outside the Earth, in that case, there will be actually a motion as well because the Earth is rotating. So this will actually move this way, isn't it? Just move that way over there. That's what will happen, which implies that if I consider with respect to this inertial reference frame, what we see in this case for the FBD of this spring, this mass actually, you notice there is a force of gravity which is going to be pulling it towards the center. That's what we have. Then we also have in this case a spring force which is just taking it up, which is actually the reading by. This is actually the reading of the scale. That's what is given, I hope, the reading. Oh, it just says weighs. Spring ship, the body has got a spring balance in the ship weighs W, which implies that W is the weight of the body as seen in this case. So it should be the reading of the spring balance, I think. There's a bit of ambiguity in this case. Usually the weight is supposed to be what? It's nothing but the force which the support exerts it. So technically speaking, then F the spring force should be the weight itself right now, isn't it? That is what I shall take up. The spring force in this case should be now the weight because this is showing written down. Obviously, we're trying to weigh it, so weighing by a spring balance will show the spring force itself. That is why I will have to consider mg, and there's a spring force. We also have a pseudo force acting if I take the reference from the Earth. But if I take the inertial reference frame, there's no pseudo force. However, with respect to inertial reference frame, I will see that the spring balance is something like this actually. So what's happening is that the block is accelerating toward the center of the Earth. With respect to the outside observer, this will be actually moving in a circular path. So this will be being pulled towards the centripetal force is the sum total of mg and fs actually. If it's not a new force, it is simply these forces which are combining to generate a net force toward the center because this is rotating in a circular path. And that is what is the centripetal force. That will be mg minus fs. In fact, mg minus fs should be the spring force over there, the centrifugal force. Is it okay? It is not going to be shown differently. You can't show the centripetal force differently as a different force. Say, obviously, if you take up the rotating reference frame, in that case, pseudo force will be shown as external force. But the centripetal force as such is nothing new. It is not a new kind of force. It's not a different force. It is same forces playing a different role. In this case, for example, mg and fs together, they should combine to give us a net force toward the center of the Earth, which will be mv square with radius, in fact. So the relevant equation then should be, because this is nothing but w, what I should write down is mg minus w is equal to m into v square upon the radius. But because the angular speed isn't given, I could write down this one as m omega square r actually. Centripetal acceleration is either omega square or v square by r. Easy to consider because v turns out that v is actually equal to omega into the radius actually. So we get that thing over there. So that gives us the reading as mg minus m omega square r. This is the reading to begin with. Okay. The next, when the ship starts moving in this direction, which is the same direction as the Earth, as that of the Earth actually. In this case, what will be the speed of the ship as seen from the external frame? It will be omega r plus v. Therefore, I will be able to write down the next time when the ship is moving. When ship is moving with a speed v from west to east, it will be, we shall have to write down mg minus the new weight, new reading effectively. That is what we have been asked. Yeah, that's what it is. New reading That will be W prime. These two together should be equal to m into the total velocity. The total velocity is omega r plus v actually. I get omega r plus v. This v is the speed with which the ship is moving. In fact, last time the v that we have taken up, let's call it as okay. Remove this part over there. Simply write down m omega square r. Okay. Last time the speed which we have used was the speed of the ship or speed of this point on the periphery of the Earth, which is omega of the Earth multiplied with the radius. This time this v is actually the speed which is given with which the ship is moving with respect to the water actually. This will be this whole square upon the radius. Visible? That is the equation we've got right now. We need to figure out W prime in terms of W, right? So I can just see from here the W prime. So I rub it up.
Please wait.
Okay. Waiting. Again. 10 minutes over, okay?
So the V and omega are in the same direction.
Weight and omega. Omega, what is the direction of omega?
The V and omega r.
Aha, in this case, the ship is moving in the, it's given, it starts to move from west to east. The Earth also rotates from west to east. So they are the same direction actually. Omega into r and v, they are the same direction, so I have added them up. Okay.
They're done.
Okay. Option 4. Let us see. Just wait a moment. We have already got these two equations. So next we
Sir,
consider
which chapter is this from?
this
Which chapter is this from?
Newton's laws. Newton's laws of motion.
Oh,
Circular motion kind of. W prime is mg minus m into omega r plus v whole square by r.
Sir, can you please tell what is W dash?
That is a new reading. There's a new weight.
Okay, sir.
This Rahul, what I have done is again, you see the forces remain. Because the ship is now moving with respect to the Earth, the net speed as seen from that external reference frame is becoming omega r plus v actually. There's the same direction. So omega r is the speed acquired due to the rotation of the Earth, and because it is already moving with respect to the Earth as well, therefore we add up v. We are adding up because they are both in the same direction. Okay, so we use the fact mv square by r. V in this case becomes omega r plus v, in fact, the speed of the ship as seen from the external observer. That is why I have got mg is a downward force which is toward the center. Then omega prime is a new reading. The spring actually will stretch a bit more. So the spring force will change and the reading will change as well. This is a new reading. Omega prime is a new reading actually. Okay, which I have to figure out in fact, which is I need to find out with in relation with W actually. So we have in this case, now what I'm going to do over here is, I will have to just, I want to compare it with the previous one. So I'm going to pull out omega square r actually. I'm just going to pull omega, this factor outside over there. So if I do that, I get m omega square r square by r. And then what is surviving is 1 plus v by omega r whole square. That's what we got. Okay. One r gets cancelled out, and you notice therefore that we get mg minus m omega square r into 1 plus v upon omega r whole square. Now, in this case, there are a couple of things that we should we need to approximate the result. Actually, the fact is this: if you consider the angular speed of the Earth, it is known in 24 hours completes one full rotation, isn't it? So the angular speed will be obtainable. It is very small, however, it is around 10 per minus 5 radian per second, something like point or rather 1.7 or 7 something. 10 per minus 5 radian per second is what we have the order as. It doesn't matter, however. The point is, if you multiply the radius of the Earth is quite large. This capital R over here is the radius of the Earth, which is 6,400 kilometer actually. So upon multiplying with that, in fact, if you remember, we earlier have obtained this. Remember, we obtained the speed of a point on the periphery of the Earth, the equator, and it was turning out to be more than the speed of sound actually. It was turning out to be around 470 meter per second, in fact, roughly half a kilometer per second, isn't it? That's quite high speed actually, because V over here will be the speed of the ship with respect to water, which will be how much? You can't expect a ship to just say move at a speed of sound over there. That doesn't happen usually. This will be more like a couple of, or in the I mean say extreme case, a couple of 100 kilometer per hour, which will not be too much compared to omega into r. The point is v, the speed of the ship, will be relatively small compared to omega into r. Okay. In fact, much smaller by the way, because omega r is, like I said, half a kilometer per second. So that makes it around how much? Half a kilometer per second. So into 60 becomes 30 kilometer per minute into 60. That makes it 1800 kilometer per hour. While the ship cannot move such fast, it's more like 80 kilometer per hour actually. That is implying therefore that v is quite small compared to omega. Therefore, what we could do in this case is we could use a very useful approximation that we have, and it is known as a binomial approximation actually. You must have studied the binomial theorem. We are doing in class 11 right now, but if you are not yet familiar, the approximation is this. It says that 1 plus x whole raised power n, that is approximately 1 plus n into x, if mod x is quite small compared to 1. This is known as a binomial approximation, okay? Binomial approximation. You see, in sciences, many times you require quite exact result because that will be scientifically accurate, but many instances, we also need to go in the opposite direction. We need to just approximate things up, okay? It's very useful. Yeah, it is used in a number of just wait.
Sir,
Yeah.
sir, can you please tell, sir, how that my m into omega r plus v whole square by r is coming that omega r plus v? I cannot understand
I
that part.
have pulled omega out of the bracket. What will happen if I pulled omega out of the bracket? Will come up the omega square r square comes out. It was
Yes,
not
sir.
over here, so omega comes denominator, isn't it?
Sir, no, sir, I was not asking that. Sir, I was asking that how is that relation coming? Sir, I cannot understand that part.
That I explained a bit earlier. I said that the net force down towards the center will become how much? Mg minus omega prime. Omega prime, so W prime. W prime is a new weight actually.
Yes, sir.
That should be equal to mv square by r should have. V in this case is speed, which is going to be omega r plus v actually. This is with respect to the external observer.
Oh, okay. Understood.
So by the way, I'll just slightly there's a painting my daughter has just done. I would like to share with you actually. I actually share because it looks very nice. So I thought I'll just share with you as well. You want to see that? Or no?
Yes, sir.
There it is. If it's visible over there. This is a painting she has just done now. It looks, well, it seems very abstract to me, but
Yes, sir, it is very nice, sir.
isn't it? That is what she just finished it, so I thought that maybe I'll share with you guys. Very interesting
Sir,
one.
has she done it with watercolors?
No, it is actually, it is in fact acrylic on canvas actually. Again,
Oh,
Shekhar, again, you want to see this? It's a bit abstract over there. देखो ये देखो. दिखा Shekhar, can you see this? I don't know what she thought, but I could see a mouth. Earth is inside. There are two, seems like eyes or a jellyfish with her eye. Like we have some planets within. The Uranus is there. Then we have the Jupiter, Saturn. Earth is inside the mouth, by the way. Okay. So they are. Okay, I'll just. Yeah, I don't know the thought behind it, by the way, but I will ask her later on, maybe. Okay. Yeah, she usually depends on mood. Sometimes she just does.
But actually, so it's very easy Can you please send a picture of that picture?
Okay, fine. I'll send you. Okay. I'll send the picture. The picture is anyway. Yes, Anik abstract art is. There are a couple of other paintings she has done. Some of them are quite striking actually. So yeah, she does have good imagination, but I hope that's not getting corrupted over there. Anyway, if I come back to this one, I was saying that we're going to utilize the binomial approximation over there, and if I, because v by omega is rather small over there, so I can utilize this particular approximation, and this could be written down as this. This is approximately, not exact, but it's approximately okay. Okay. And now if I open the bracket over there, well, it's turning out to be negative, it seems. That should be a bit minus. It's coming negative. How can that happen? The equations are mg minus w prime was equal to this thing. Well, should have been plus v or minus v either. Now I'm getting, strictly speaking, it should have been what? Mg minus w prime. W prime should increase actually, isn't it? It should have increased. Mine one is decreasing in fact. If the speed becomes more, the stretch will be more as well. If the stretch is more, then W prime should actually increase. And if you've written down the previous thing, what I wrote down, W equal to mg minus m omega square r was there?
Sir, but W prime should decrease, I think, because sir, here previously it was m omega square r, but here it is m omega r plus v whole square by r. Means it is more than the previous
okay,
one.
fine. It's fine. It's fine. I was just thinking this would become 0. It won't become 0. It will become W actually. So yeah, it's fine. It will be in fact. I mean, say. Can you repeat? Oh, yeah. That we are subtracting more in fact, so it should be decreasing. That's fine. That's fine. Actually, I was thinking this part becomes 0. It won't be 0. It will be actually W itself. So we get what? I get mg minus m omega square minus, open the bracket, omega r cancels out, we get twice m v omega. Yeah. So this part is simply w. That is w minus twice m v omega. And I can pull out w common, though they are using w as mg, it's not exactly correct. However, we can use that because omega square is very small actually. Omega square terms of use it. If you look at this portion, omega square r. Okay, let me first of all write it down. So far it is okay. I'm just rubbing this part. Okay, the top part over there. I think it have been done by everyone. This becomes what? W prime. Therefore, becomes w common 1 minus twice mv omega by w. Now notice that w was mg minus m omega square. Okay. Now if you look at, compare the values, there are something that you should actually keep in mind over there. This is actually coming up. If I plug the value of w, it is mg minus m omega square r. However, if you compare the values of g, which is around 10 meter per second square, and omega square r, omega square terms are very small actually. It's turning out around 0.3 something meter per second square, rather small. Okay, if you in fact consider the value exactly, omega is 2 pi by 24 hours, 24 into 60 into 60 seconds. There's omega whole square into the radius, 6400 kilometers. So that makes it 1000 meters. This is turning out to be actually 0.034 rather. If I just look at omega square r, the value of omega square into r, that value actually is very small for the Earth. For the Earth, the omega square r is turning out to be approximately 0.034 meter per second square, which is very small compared to g actually, which implies I could safely neglect this factor over here and just write it down. In fact, we could have just neglected this part from the very beginning. It will not be mattering much. So the result is we end up getting this as w into 1 minus twice mv omega by mg only. I can neglect the second part over there. It's also an approximation we have in this case. And therefore, the end result is turning out to be w into 1 minus twice v omega by g. That's what I have, okay? Which is going to be the option number. Okay, I've simplified it. So for your question, this will be enough, right? This part will be enough, okay? Option number 4 is what we have. I simplified it. It's not required in any case, right? That is fine as well, okay? Okay, Rahul, you got it. Rahul is here, I hope. Yeah, Rahul is here. Fine. Then seems today we shall have a doubt session. Doesn't matter. Let it to that. Ryan has sent a question for both 3 and 4. Both 3 and 4. No, 3 is some other option. 3 is containing plus sign. It won't be plus. It will be fourth option. It is containing plus sign. We require a minus sign actually. Yeah, that's what happened.
So last day you had given one homework. Finding the maximum angle theta. That one.
For which? Maximum angle theta?
So for a pendulum, maximum deflection means the angle theta for a pendulum. If a force F is
just wait. There's another question which is in fact coming from the work energy principle. Let's take that one up, and then I will talk about it. Okay. This question is from this this particular topic that we're dealing with right now. It will be useful. It actually involves both the current topic and Newton's laws of motion. Let's deal with this first.
So is the answer to that question 90 degrees maximum deflection, and for the equilibrium for position it is 45 degrees?
No. Oh. What was no? How can it 45? There was a force F which was acting. F was not given. It was just given F.
Yes, I was just telling about the maximum value. That means I just considered that acceleration, the acceleration which was given by the external force as g, and then
G,
found out
why
the.
G?
Sir, I first of all I derived the expression for that pendulum, and then I took the value as g, and then I.
No, that cannot be taken as G. Point is that force was not mg. The force was F. F was the horizontal force which is acting, isn't it? You can't take this as mg. It was given F itself, so it will be coming in terms of F.
Oh.
Yeah, but we can actually do many things, by the way. I'll talk about it in a moment. Let's finish this question.
Sir, in this question, can you show the direction of the means angular velocity, not angular velocity, omega r square, that one.
Omega is square r. That will be toward the center of the earth. What else?
Oh yes. Okay, sir.
Moving in a circular path, center of the earth, centripetal acceleration. The next question that we have is, as I said, it was sent. Let's consider the situation is this: we have actually a block of some, say A, which is tied to a. Actually, we just admitted to you what happened. It's facing a lot of problem normally. A3 has. Right. Okay. In this case, the question is that we have a block A whose mass maybe is m, for example, and there's another identical block, which is this block lies on a frictionless table. Actually, table is frictionless. It is tied to another block of same mass, which is B. It has same mass m, that of A. The thread which is tying this block A to the table surface, that's what setting is right now. The value which has been given, the spring constant is K, and initially the spring is unstressed. Initially the spring is unstressed. There is no elongation or compression. The spring constant is given as K, which is given as 5 mg by L naught. K in this case is 5 mg by L naught. L naught being the natural length of the spring. L naught is equal to natural length. Natural length of the spring, which implies the length in unstressed conditions. Okay. The block B has a mass which is same as that of A, which is not given actually. M, which is given M.
Sir,
Yes.
sir, is the general relation to the question which I was speaking about is G is equal to G cos theta plus A sin theta. A is the acceleration, means which is given by the force, is the acceleration which is produced.
You could say that. General expression implies what, the effective gravity talking about?
Yes, sir.
Well, it will be simply, in this
Sir,
case, the root of G square plus A square actually, in the given situation that I asked last time actually.
okay.
I said already, very early, I said that a constant acceleration can be treated as a uniform gravity in the opposite direction, isn't it? Let's first finish this one, then I'm talking about this, okay?
Okay, sir.
We can consider this pulley and the threads to be massless, and we should also assume there's no friction anywhere, okay? So what is done is this thread is burned. I just burned this thread, and the entire system starts to move. Initially, everything is stationary. The spring is unstressed. There's no stretching or compression. Then this thread over here is burned. Once this thread is burned, P. Once AP is burned, the system starts to move. We need to figure out the speed of the block A, this one. Ink has gone. Find speed of A at the instant, at the moment when it lifts off. When it lifts off, O-double-F off the table. We have going again up a bit. The question says once the thread AP has been burned through, the system starts to move. You have to find out the speed of the block A at the instant it loses contact with the table. It basically lifts off from this table. Why it's going to lift off, it will be also discussed right now. So we need to figure out the speed of the block A. It will be same for B as well. At the instant it lifts off the table. Okay, there's a question. And before actually writing down the equation that you need over there, it is useful to consider the analysis of the situation. What might be happening in this case once the thread P has been burned through? If I just burn the thread, how will the system move subsequently? We notice in this case that once this particular thread is burned, it's no longer there. Earlier it was there to prevent the block A from moving, but now it is no longer able to prevent it because the block B is going to pull it. So what will happen is it's going to pull it down, and A will start moving this way. But as A move that way, the spring is going to get stretched, isn't it? The spring is stretching. As it stretches, the spring force increases. So as it keeps on going this way, the spring force will be actually tilted, but will have a component in the vertically upward direction. So that reduces the normal reaction. So as it goes more and more, the spring pulls more and more, and at some point of time, the spring force is enough to lift the A off the table. When that happens at that very moment, at that particular point, mg of the block A will be exactly equal to the spring force vertical component. Okay, so we can utilize that condition to find an equation where we end up getting the angle at which the quantity is broken. Then we can obtain the energy conservation. The idea is that if I take the spring, the block, this block together as one system, then the energy remains conserved because there's nothing external being done. Because my spring is part of a system, A and B, they're also part of my system. The thread is obviously an internal force, can't do any work over there. The table force, the normal reaction cannot do any work because the force is perpendicular displacement. And this obviously at this contact, there is no work being done because it's fixed over there, which implies that total energy remains a conserved quantity. And therefore, what happens is, if this block goes down by a certain amount, the loss in potential energy is going to appear as increment in the kinetic energy for both these blocks, as well as increment in the spring potential energy over there. Fine. We can utilize that idea, write an equation that will give us the required speed of the block A and B as well. They're the same actually. Okay? The entire procedure. So we first start at that condition at which point the quantity has been broken. Take that angle as theta. When the quantity is broken over here, consider the angle to be theta over there, this angle. At this point of time, the elongation will be in terms of theta, and then upward force component is known to be exactly mg. Utilize that to obtain the condition for theta, cos theta rather. Okay, and then proceed a bit. I'll just refill the ink. I'll give you some time to finish it off. You should always think of the work energy as I was saying last day itself in other batch. The work energy principle or work energy rather can be always thought of as money if you are comfortable with that. The changes you can always see. This has a lot of similarity with money actually. I mean, especially the money which is not the physical currency but the virtual, which is nowadays going to be quite common. Okay, we can let's see later on. It seems that in near future it may happen that the society is entirely cashless. All the dealings are in terms of the virtual money, the numbers. So there will be no money technically speaking. It will be just some set of numbers, ultimately, isn't it? So in that case, it will hardly matter. I mean, say only the transactions can be seen. Exactly how much amount somebody has can't be seen in that case very easily. Obviously, it's now also not visible very easily. But once that particular idea is utilized, we notice that it is at transactions which will give us the indication of the amount actually. The transaction can always be seen. Same thing is with the energy itself. The energy itself is an abstract quantity, okay? There's nothing called energy if you wish. It is just an abstract quantity. You can say just a bit of numbers. And ultimately what we will have to do is just to calculate some numbers. The changes can be seen, but the energy itself cannot be. There's nothing called absolute energy. There's nothing called energy if you want to just talk about that, because nobody can see energy as such, but the changes can always be calculated or measured actually. So the changes are what is important over there. Fine. The idea of energy itself is a bit of abstract over there. It could have been anything over there, but we chose the energy to be that object, a particular abstract quantity. We say it is conserved, but nobody knows exactly how much it is in the universe, isn't it? We just say total is conserved, but exactly how much it is, do not know. That's what the idea is with money as well. So the same thing can be, if you're good at accountancy, then definitely you could apply the energy conservation principle. So work energy principle, good enough. Very early, some people asked what is energy. I wrote down an answer in a website called Quora. If you notice this, I think you know that QUORA, isn't it? There's a website.
Yes, sir.
Yeah, so I wrote an answer for this question very early. Maybe I'll just copy paste that answer in WhatsApp group sometimes. You could read. Somebody asked what is energy. So that was my answer. You are registered. Okay. You can find my name, I believe, if you search for it, and the questions and answers as well. But I'm not registered as Anant over there. My login name is KYMNT. With that name, I just am registered as well. So have you done it? Any one of you got something? Okay, waiting. Uh, what about the paradox? What the paradox which was dealing with that inclined plane? Or what? Anik, which paradox talking about? Energy. Well, I don't remember talking about any paradox regarding that. Did I say something? Do you remember the paradox which I don't think that I have talked about any paradox in energy. I just gave an example where the energy was seemingly not conserved because we applied the work energy principle wrongly, in fact. Yeah, but I said, for that case, I said that there was no paradox in the moving reference frame because, yeah, the work done by the normal reaction was the one which was decreasing energy. If you look carefully, the path of that object was not, in fact, normal to the inclined surface. In the other reference frame, it was actually at an angle. The angle was obtuse, in fact, between the normal reaction and displacement. The work done was negative, which was the one which was losing the energy, actually. And that negative work by the normal reaction was what caused the energy of the body to be lost, actually. there was no paradox. Obviously, there's nothing like a paradox if you think or if you kind of consider corrective situations. है ना? It has gone where, by the way? Just wait a moment. If you are saying something, I'm not looking at the meet right now. Just a moment. I'll come to that. Yeah. 1 centimeter per second. Ryan is here. Yeah.
Yes, sir.
The answer,
Yes, sir. 1.7 meter. That is answer. 7 meter.
ठीक है, it's okay. Ryan, did you try it again?
Yes, sir. Trying but not getting the result.
Okay, no problem. ठीक है, Anik, you can leave for that wellness session. Okay. Be well. What else? See, what I was saying is, quite obviously, when the body moves, say, for example, this distance comes over here, A, then obviously
Sir.
the. हाँ, बोलो.
Sir, I have got a relation, sir, which is, sir, let's say the block M moves a distance h. So then if we apply work energy theorem and derive the relation, sir, I am getting mgh plus mgh minus in bracket mg sine theta plus ma into cos theta
A
into
is
h.
what? A is what?
Sir, a is the acceleration of the system.
In this case.
Yes, sir.
And how much will that? And why are you taking M into A into something? I mean, there is nothing called pseudo force in this case.
No, sir, not the pseudo force, sir. It is the work done by the spring force.
Then you cannot take the energy of the spring into account then. And that will be difficult because the spring force is variable in this case actually. We can't
Yes,
take
sir.
it as a constant. So that's a wrong equation in any case, by the way. Okay. Because the force of the spring is variable in fact. So it is useful not to take in terms of force but in terms of energy. That's easier. We know that energy of the spring is half kx square.
Oh.
3 hours, 1 minute before I was just asking the answer from Ryan actually. And I was just going to discuss it over there. Fine. You haven't missed much actually. 1 minute I didn't do anything over there. So in this case, what I said is one thing which is quite easy to see is that these two blocks they always move the same distance actually. So if I assume that the block has gone down by h at the moment when the contact is broken, fine. This will also go in that way by h itself. This will also go this distance by h itself because they are tied with a thread. So they must traverse the same distance horizontally that vertically. Fine. They're equal actually. Now what we notice over here is if I take this angle theta for the moment, at this point I'm assuming the contact to be broken. Fine. At this point, assume that the contact is lost. The spring force will point in this direction. The spring force pointing. I know in this case that the spring force is a vertical component which is exactly equal to mg because that is why the normalization becomes 0. There are two forces acting on the block A where the spring force and the gravity and thread tension obviously, but the vertical force we have only two, gravity and the component of the spring force, and the normalization is going to be there as well. But the moment when n becomes 0, Fs, the component in the vertical direction, should be exactly equal to mg. So that would be my starting point at the instant the contact is broken, or the block A lifts lifts off the surface, lifts off. At this moment, what's going to happen? Fs, this angle theta, this is theta as well. So Fs cos theta, that must be equal to mg. This must happen. Otherwise, it will not be able to balance. But what about the spring force? I noticed, but the spring force that will be given by k into the elongation of the spring, isn't it? What are the elongation?
Why there will be no reaction force?
That will become zero at the point it's losing contact, isn't it? I'm considering the
Yes,
moment when the lift off is there, at the exactly same moment I'm talking about. So that point n will become zero
Yes.
because. Okay, fine. So I say that spring force is going to be k into the elongation. The elongation becomes how much? I know this is L naught. And what about this one? That becomes L naught by cos theta. Because you can see this length into cos, because that's a right triangle effectively. So this hypotenuse into cos theta should have been L naught. So hypotenuse becomes L naught by cos theta actually. So elongation therefore turns out to be L naught upon cos theta minus L naught. That is elongation. Which I could therefore, if I consider that mg has to be equal to fs into cos theta, that gives us k L naught into 1 minus cos theta by cos theta into cos theta. I have simplified this one, L naught pulled out 1 minus cos theta by cos theta, and this cos theta comes because of the fs cos theta over there. So therefore mg must be equal to this. I can see that cos theta cancels out. This will give us therefore that mg by k into L naught, that is turning out to be 1 minus cos theta. This is mg by k L naught, but we have been given that k was 5 times mg by L naught. This was what been given, isn't it? This was given to us, which implies that mg by k L naught is just 1 by 5. This becomes 1 by 5 equal to 1 minus cos theta, giving us cos theta is 4 by 5 actually. So that gives us cos theta is equal to 4 by 5, which implies the moment the contact is broken, the angle theta is determined by this particular relationship, that cos theta is equal to 4 by 5. Over there. Okay. I know this, therefore I can actually find h as well, because cos theta is 4 by 5, base by hypotenuse is 4 by 5, so the altitude is going to be 3 in fact. So that implies that tan theta becomes 3 by 4 in this case. In fact, it will be around 37 degrees roughly, cos theta, theta rather. So we know cos theta now, and therefore I know the elongation as well. I in fact know most of the things. I still know how much is elongation. Elongation becomes L naught by cos theta, which implies L naught, and 5 L naught by 4 minus L naught, which implies L naught by 4 itself. That's the elongation of the spring. And this will be also known. H by L naught is tan theta in fact. So H is L naught tan theta. Okay, fine. I just send it a moment. Wait. It's coming hazy.
yes, sir, too much.
Okay. I'll just move by this. So please. Yeah. There is a screenshot I sent. Okay, so I was saying that once we figure out cos theta now, we could consider the elongation as this elongation. The length of the spring will become known now. In fact, this is elongation. In fact, this is elongation. The elongation is going to be L naught by 4 by 5, which implies 5 L naught by 4 minus L naught becomes L naught by 4 only, which implies the elongation is known, and we also know this one. H by L naught is tan theta, which is 3 by 4. So H becomes 3/4 of L naught in fact. So we know therefore how much potential energy is being lost by this block. And so we can just finish it up now. Hope it is okay. Therefore we have got, therefore spring elongation that is turning out to be L naught by cos theta minus L naught. That gives us 5 by 4 minus 1 is 1 by 4. So I get L naught by 4. That's a spring elongation. And also the value of H is known. And H is in fact L naught tan theta. Tan theta is 3 by 4. So I get this to be 3 L naught by 4. And finally, we could apply the work energy principle. I notice that since no work is being done, the energy is remaining conserved actually. Taking my system as the block A and B and the spring together. For the system consisting of, I'll just write down A plus B plus the spring as a whole. I mean, including the earth as well, including the earth. That is my system in this case. Earth is coming up because we're looking at the gravitational force. It's part of the system, in fact. This is, for this system, the energy is remaining conserved, in fact. The mechanical energy is conserved. Mechanical energy is conserved. And therefore we could consider in this case the loss in the gravitation potential energy by the block. So if I write down, therefore the loss in the gravitational potential energy of B should appear as, because total is not changing, so whatever B loses will be gained by everything else. Okay, so it appears or appear as the kinetic energy of A, B, and the spring energy is visible. I hope I just take a picture. And the spring energy and the elastic spring energy, spring elastic energy. We have, right? Therefore, we could just a moment again.
Yes, sir, it's visible.
It is visible now. I should take a picture over there.
Sir, I have written heading your words.
Okay, fine. In any case, I will send a picture. So we can now finish it up because we can just write down mg into h is equal to half mv square plus half mv square for the two blocks and half k into L naught by 4 whole square. Okay, so that will give us, we already have a relation between mg and k L naught in fact. So the final statement therefore, I'm just putting the system over there. mgh, h was 3 by, okay, let me do 2 steps, will be double of half mv square and then plus half k into elongation square delta L square. I'm writing down for the spring. Delta L implies elongation. Okay, this gives us mg into 3 by 4 L naught equal to m into v square plus half k. Elongation is L naught whole square by 16 because L naught by 4 was elongation in fact. That's what we have. Now from there we could use well, we can use the fact in this case that KL naught is nothing but 5 mg. That is what we can use. So I could replace this becomes 3 by 4 mg L naught equal to mv square plus 1 by 2 into KL naught becomes 5 mg. So I get 5 mg L naught by 16. M can be cancelled throughout. So that gives us V square equal to 3 by 4 minus 5 by 32 into GL naught. And that will become 8 for 32, 24 minus 5, which is 19 by 32 into GL naught. Anything else was given information?
Sir, L naught is
50
given 50
centimeters.
centimeters.
Yes. L naught is 50 and G is no. 50 implies half meters actually. The G has taken as 10. So if I take G as 10, I get 5. 19 by 32 into 10 into half. That is what I've got. So it's very, very close to, yeah, okay, that's fine. So V will turn out to be finally 19 into 190 by 2. That is, 50,
95.
95 here by 32. It's not very close to 32. We know the square root. 4 root 2 is what we have, but limit 95 is close to 10 approximately. If I just do that approximation, then I have got 1 by 4. 1 by root 2 is roughly 0.707, 0.7 approximately. Yeah, that's fine. How much are you getting, Shekhar? 0.304 is what? Is a speed or what?
So 95 by 32 is approximately coming 2.9. Like that.
Okay, 190. Sorry, 95 by 32, isn't it?
So it is approximately coming 1.72.
Uh-huh.
Okay. Yeah, 1.72. 1.72 meters per second. So that will be approximately 1.7 meters per second. है ना? Yes, we have.
Yes, sir.
Yes, sir.
Okay. Bolo.
Sir, in this numerical, you told us the method and we could solve it. But in case of any unknown question, how to realize that whether we should use work energy principle or Newton's laws of motion?
You see, you should make it a habit to always apply the conservation laws first. If they're applicable, you'll get the required result quite easily. So after a couple of tries, if it's not coming, they'll have to go back to dynamics. In this case, why I didn't try to use dynamics, because the spring force was variable. First of all, the component also variable. So finding the, by force method becomes quite complicated actually, because the force is a variable one. So that is why I looked for the energy principles. Okay. As I was saying, the thing that you could do is to make it a habit to always go for the conservation laws first, and try to first attempt them. If obviously it is in context, then you can always say, if it's already given in the conservation law chapter, then you can do that. But in an unknown situation, I'm talking about, if you just get some question which is do not know from what topic it is, a mechanical problem, but you do not know the topic, then depending on what's being asked, usually first of all the conservation law should be utilized. Yes, Anik, you can leave. Okay, you can leave. This is much more useful, in fact, okay, compared to dynamics. As I said, if it is applicable, you'll get the required result very easily. So you will not lose much time over there. And they'll obviously require some practice. By practice, you can see that, okay, which thing requires what actually. There are in fact 3 conservation laws that we shall be using. We have already taken up 2 of them, energy and the momentum. We haven't talked about yet the angular momentum, which is going to come after the rotation part actually. These 3 are the usual conservation laws in case of mechanics. So I think it will be. Shubham, in the last 15 minutes we just did this sum, so maybe I'll just complete the entire thing by taking a snapshot for this one as well. You can just look at the screenshot that I have shared. Okay. That is finished. Yeah, this is a question you have attended so far actually. Last 50 minutes. Okay. Okay. Which I've got 3460. Wait a moment. Okay, let us take up who was there. Rishabh, I think, sent some question. This is from Dynamics. And again, Rishabh, this question that you have sent. Okay, I don't. I should rub this up. Just do that Rishabh's question quickly. You have to just balance the forces. This question I think people have seen already. Whatever, there's a person who is being pulled by two of his friends from a ditch. I don't know how he come to fall in a ditch over there. Like this. The man over here is just.
Sir, this is from AC Verma.
Yeah. Yeah. The question says that a man is falling to ditch of width. Yes. Somebody saying something? I'll just give you a hint, Rishabh, in this case. This question is just requires the force balance actually. Just you see that the ditch has been given to be d wide over there, which implies that we know exactly that this is going to be d, but the diagram is a bit asymmetrical. Shifted a bit over there, this side. So this one is d by 2, and height is given as well from here to here. The height is given. You could see in this case that this angle can be figured out. This angle, and the force which the persons are applying, the same force has to be this way as well. The same force on this way as well. So you can just look at the component F into cos of this angle. This angle is same thing as this angle, which I can find from diagram. Okay, so F cos theta from the other side also comes to twice of F cos theta.
So what to find in this case?
Oh, you don't know the question? The question is to find out the force which the man must, with the two friend must exert to. Oh, this question not in the group by the way. Sorry.
Sir, the force is coming mg by 2 cos theta.
Yeah, I'm just in the question now in the group. Yes, it will be actually just balance the force, upward force on the rope on the man with equal to mg actually. One force is this way, one force is that way. They're both exerting the same force, and therefore twice F cos theta have to be equal to mg. So F becomes mg by 2 cos theta, and then you can find cos theta from the given geometry actually. This is h and this is d by 2. Okay, as we have. Rishabh is fine. So couldn't take anything more today. Doesn't matter. Rahul's question is done, I believe. No. Yeah. Anybody needs to ask anything else? Your question is done, Rahul. Here. So anybody needs to ask anything else? If not, then we can. I think that I'll finish it early today. Next class I'll inform. Okay, possibly Thursday morning will not be possible. I will inform about the next class. try to see when I can have that. Yes, Rishabh, saying something. And the next topic I'll be doing will be the collisions over there we haven't taken yet. That is one part I need to look at. No, I'm not giving. I won't give Thursday morning. At least I won't give. Evening I don't have time. Maybe I'll just have a couple of days for holidays for you. At least this weekend till that weekend. Then after that we can try. Your school's holidays are, by the way, do you know when are they reopening? The school holidays will start from, I think, next, 22nd, I believe, isn't it? No, yes, something. Second or third. And when they are going to reopen, can you tell me? DAV, Hemshila, the other schools?
No.
So after reopening, Hemshila and she will be having exams. Means so.
Oh, second
Third, I
November.
Sir, might be after this puja.
Okay. So I'm just asking till when are the holidays?
Hemshila is up to November.
Till
November.
November implies what?
No, means till the beginning of November.
Implies 1st November, and from 2nd the exam starts.
Yes, sir.
Okay. And DAV?
Sir, no information is out till now. Sir, I believe that the school will reopen after this puja.
I don't think they'll open after the puja directly. But it's okay, no problem. In that case, maybe you can manage some additional classes after the holidays are over. After puja is over, actually, not the holidays, but the puja is over. At least I think, say that we shall give a break over there. But I'll confirm over WhatsApp. Okay, I'll just confirm the final thing. And once we take up the next class, we shall be working with the work. These collisions over there. And I have sent you some questions in work energy. You get the time, then try to finish it up. Okay. And apart from there, anything else somebody needs to ask, then it is okay. Otherwise, we shall finish now. Today a bit early.
So last homework.
What?
Last day's homework that you gave.
Oh, yeah. And Rishabh, in this case, why it happens? Because the force components must be balancing. You see that this force F is acting this direction, the same force acts in this direction. I'm just using the symmetry of the problem actually. I'm assuming things are symmetrical. This angle is theta, there is also theta as well. We get F cos theta from the left end and F cos theta from the right hand. This is the vertical component. The horizontal component just cancel out in any case, by the way, because they are going to be same in opposite directions. So they just cancel out. And what is left is therefore just the vertical components. Okay. And that is why I've equated, because the man over here is basically pulled very slowly, which implies that he is going to be at equilibrium. Net force must be 0. That is why twice F cos theta and mg should be balanced. Is it okay? I hope it is okay, Rishabh. I lumped it up. Yeah, that's fine. Achha, regarding the question which I gave as a homework, you see there are multiple ways that you could do it actually. One possible way, one way is to apply the work energy principle. The fact is, with this force F which is acting always, it's going to do because a constant force, if the maximum deflection angle I consider this to be theta, for example, the maximum deflection angle is theta. In that case, F multiplied by this length, the horizontal displacement, that is going to be worked done by this force F, and that should be equal to the increment in the potential energy only, because the kinetic energy is simply 0 at the end, and initially it was 0 as well. So I could write down therefore that if the length is L, then L sine theta is the displacement. So F into L sine theta, that is the work done by this force F. This must be equal to the increment in the gravitation potential energy which is mg into this height. This height is nothing but L minus L cos theta. So L into 1 minus cos theta. That we have. And from here we can just solve for theta. If we have maximum deflection, I'll have to just do a bit of work in this case. But this equation will give us the required result. Okay. The other thing that
Yeah, I also got this only.
fine, then it is okay. Just try to obtain theta from there. Okay. The other thing that you could do is to consider the effective gravity. Actually, if you always notice, remember that any kind of constant force can be thought of as a gravity in the opposite direction. Actually, in this case, because just not the constant force, but the acceleration. The acceleration is equivalent to gravity in opposite direction. In this case, actually, this force will create an effect of a gravity itself, but a horizontal gravity. You might think. The previous statement was applicable in a different situation, by the way. In this case, we have a constant force acting. We might think of like a gravity actually. You might think, okay, there is some kind of gravity acts in this direction. Okay. So the net gravity is going to change. Net gravity will be the resultant of F by M and G actually. So F by M acts horizontally. This is the effective, another kind of acceleration to gravity. And this will, the G will be usually acting down. So the resultant will be the net gravity as seen by the pendulum bob. And therefore at equilibrium, it will try to align in that direction. I can figure it out. This angle, if I take it as alpha, for example, in that case, I get tan alpha equal to F by M upon G, which apply F by mg. That is the net direction or the direction of net gravity. So the pendulum bob will try to orient in this direction if you just leave it slowly. Okay, we know in this case, and you like something that if you just take a mass deflect the pendulum this way and release it, it will just go down. Obviously, won't come to rest over, it will go to the other side. However, the equilibrium position is the vertical downward position. But in this case, because the effective gravity we have, the vertical has changed. The vertical is no longer this, but rather this way. So if I leave the system slowly, then the pendulum bob will orient itself in that direction. Okay, so you can figure an angle out alpha, but then deflection will be twice of that angle because the equilibrium it not come to rest at equilibrium. We just go overshoot, go to double the entire thing. So the resulting answer will be nothing but double this angle alpha, and tan alpha is given by F by mg. So double of that angle becomes the required maximum deflection action. Okay. The other ways as well, you can construct a gravitation, you can construct a potential energy for this constant force F as well. But leave it for the moment. It will be same equation of work done. The required answer I have said both this method will give us the required result. Okay, any one you can consider.
So can you explain the second process once more?
Yeah, I said in this case I'm going to think of this force as if it was some kind of gravity, additional gravity, because the gravitation generates a constant force of mg. There's also a constant force F. So I can think, okay, maybe that we have another kind of gravity coming up. Okay, and that is F over there. So we have effectively now two gravity. Acceleration to gravity will be G for vertical and F by M horizontal. They two together will give us the required net acceleration due to gravity. Fine. That I figure it out. The resultant of these two at a certain angle. This becomes a new vertical for a pendulum bob actually. Because net gravity is that when we always set vertical with the net gravity in fact. Okay. And that is why the net gravity as seen by the pendulum bob is no longer vertically downwards for us, but will be this way. And that behaves like a new vertical for a pendulum bob. So now the question is as if we have released the pendulum bob from angle and leave it. So it just overshoot, go to middle position, then overshoot the other direction, same amount. In this case, only thing which is happening is now the equilibrium position is no longer this, but actually this. This is the equilibrium position now. Fine. So it has released from here to try to go towards the equilibrium position, but overshoot, go to the other side, come back, and so on. So the point is that you figure out the equilibrium angle and make it double to get the maximum deflection. Is it okay? Because motion is symmetric always in the gravitation, uniform gravitation. Is it fine?
Yes, sir.
It can always be done for a constant force actually. Okay. In that case, we shall be finishing it today over there. Okay.
Okay, sir.
Yeah.